Hi, welcome to the screencast. I'm trying something different here. I'm going to try and annotate as we go. Um, so, just to set the table where we're talking about the regulation of anterior pituitary hormones. So, it's the anterior pituitary we care about. And in each case, we're going to start with the hypothalamus is going to release, come on, there we go, some sort of regulatory hormone that's going to hit the anterior pituitary that is then going to release some other hormone, which is going to hit our target organ. Our target organ will then release what I'm calling like the end product hormone. And then there's going to be some sort of feedback. It might be positive feedback, it might be negative feedback. It doesn't matter. We're going to have this same loop where it's the hypothalamus communicates with the pituitary, causes it to release a hormone, which then hits a target organ, which produces an end hormone that affects the whole body, and then also feeds back on the hypothalamus to ultimately regulate the levels of that end hormone is what we're trying to get to. But right now we're just talking about the anterior pituitary hormones. So next up we have two anterior pituitary hormones that are regulated together: follicle stimulating hormone and luteinizing hormone. Their functions are listed here, but you don't need to worry about their functions. As this says here, they're both absent before puberty, and then in both boys and girls, they start cycling during puberty. So we are going to see that LH and FSH are governed by the hypothalamic hormone gonadotropin releasing hormone. So we'll start with our friend, the hypothalamus. I'm not going to write hypothalamus because it'll take too long. That is going to release gonadotropin releasing hormone, which will travel. We'll get the travel in there and we'll get the release here, right, to the pituitary. Hey, this is working out pretty well. And then the pituitary is going to release LH and FSH. It's LH that we're really worried about, but we can talk about them both together. So they are going to go to the gonads. So this is testes in males and ovaries in females. So then what's going to come out of the gonads is either testosterone or estrogen. And then that's going to feed back on the hypothalamus. And I'm going to do a positive and a negative because depending on the timing of the cycle, estrogen either causes the release of more GnRH or less GnRH. We're not going to get into the details of exactly when that happens, not even when we do the whole chapter on reproduction. So again, the hypothalamus is going to release gonadotropin releasing hormone, which travels to our anterior pituitary, causing the release of LH and FSH, our gonadotropins. They are going to stimulate the gonads, that's what gonadotropin means, to release hormones, testosterone and estrogen, and then they are going to feed back on the hypothalamus, sometimes negative feedback, sometimes positive feedback. Okay, now we are on to growth hormone. I don't know if there was an auditory hiccup there. I had a little technical issue on my end. And there we go. Sorry, just trying to get my editing tools up there. So now we're on to growth hormone. Growth hormone we're going to do in sort of two parts. One, we're just going to talk about the regulation of growth hormone, like our other anterior pituitary hormones. Then we're going to talk about all of the effects that growth hormone has on the body. There's going to be direct effects and indirect effects. So growth hormone, we're going to do the whole story of growth hormone. We're not going to stop at just its regulation like we did with LH and FSH. So as usual, let me get my marker. There we go. It's going to start at the hypothalamus. When your hypothalamus decides you need to grow, it is going to release growth hormone releasing hormone, which will then travel to the pituitary. Which will release our friend growth hormone. One of the things growth hormone does is it targets the liver. And when growth hormone hits the liver, these things come out, insulin-like growth factors, which I am just going to call IGFs. They are called insulin-like growth factors because they ultimately end up lowering your blood sugar, which insulin does as well, but these do it by a different way. So then insulin-like growth factors and growth hormone are going to negatively feed back on the hypothalamus. And additionally, they are going to cause the release of growth hormone inhibiting hormone, GHIH, which is going to block the pituitary from releasing growth hormone. I could make that prettier, but it would take me too long. So that's the whole growth hormone pathway. Hypothalamus releases growth hormone releasing hormone, which stimulates the pituitary to release growth hormone. That targets the liver, and the liver releases insulin-like growth factors. Then both growth hormone and insulin-like growth factors, when they get to high enough levels, cause the hypothalamus to make growth hormone inhibiting hormone, which is going to block the production of GH once your GH levels get high enough. So then we have to go into what are the whole body effects of growth hormone. And we're going to have indirect effects and direct effects. Direct effects mean that these things happen when growth hormone hits these tissues. So when fat cells are exposed to growth hormone, they break down fat and release fat from your long-term energy stores because you're growing, and growing takes time and requires energy. Growth hormone also increases your blood glucose levels by causing glycogen to be broken down. Glycogen, you will remember, is a polymer of glucose, so you break it up into glucose molecules. Now you're releasing fat and glucose, which is energy for the body. And as we already said, growth hormone causes the production of insulin-like growth factors. Then it's what the insulin-like growth factors do that we refer to as indirect effects of growth hormone. So the insulin-like growth factors actually cause the growth. So mitosis in cartilage and bone. So this is how all of your long bones get longer and how bones get thicker. And then protein synthesis in muscle. This is how your muscles get bigger. Each muscle cell generates more protein fibers and gets stronger. You generally have the same number of muscle cells throughout your adult life. Then there's this table. We don't care about the table. You can go over it, but it would be boring for me to do so, I think, here in this screencast. And it goes through the same things I went through. It's just you have this arrow for your direct effects, and then insulin-like growth factors. These are your indirect effects. So you can have imbalances in growth hormone. How they're referred to has to do with both like the timing and whether it's too much or too little. So this woman right here is grown. She's in her 20s. I think she has a reality TV show. I forget who she is. But she is rather short. She has what is called pituitary dwarfism. There are other kinds of dwarfism, like achondroplastic dwarfism. In pituitary dwarfism, all of your features and proportions remain the same. You're just smaller. Then this is a pituitary giant. This looks like somebody that just had too much growth hormone during childhood and puberty, so they got tall, but then their growth hormone levels decreased the way they're supposed to. So they're tall, but their features are normal. This is Andre the Giant. Andre the Giant has acromegaly. So you can get acromegaly where you're a normal height and your growth hormone levels never decrease. So you do end up not growing anymore because testosterone and estrogen are involved. But because you continue to produce growth hormone into your adulthood, your hands get thicker and your facial features change. Andre here, who some of you may remember, was a professional wrestler and sometime actor. He had gigantism and acromegaly. So he had too much growth hormone growing up and too much growth hormone throughout his adult life. And that is growth hormone. We are going to skip these. These we'll just do when we're live in class. Then we get on to thyroid stimulating hormone. This, as it says up here, stimulates the production of thyroid hormone from the thyroid glands. We're going to talk about what thyroid hormone does after we talk about TSH, but we are going to go from TSH right into thyroid hormone because this is our last anterior pituitary hormone. And I just made a new slide with just this text so I had more room to write. So again, we're back with our friend, the hypothalamus. When your hypothalamus thinks you need more thyroid hormone, it releases what is called TRH. So TRH stands for TSH releasing hormone. That is the TRH. It's confusing. When TRH hits the pituitary, it causes the release of TSH. So when you're studying for lab, you want to remember thyroid stimulating hormone comes from the pituitary, stimulates the thyroid. That's a common mistake on the lab quiz. So the hypothalamus releases TRH, which causes the pituitary to release TSH. TSH is going to stimulate your thyroid gland. Whoops. Pretend I can write. There we go. And your thyroid, we are just going to say for now, produces thyroid hormone. There are two of them. We don't care about the difference between the two at this point. And then the wrinkle for TSH is that there's negative feedback at both the level of the hypothalamus and the pituitary. So when your thyroid hormones get to a high enough level, they block the release of TRH and TSH. Presumably this is because your thyroid hormones have big effects on your metabolism and they happen quickly, so you need to tightly regulate your thyroid hormone levels. And this is just a diagram showing the same stuff. Okay, so now we are out of the anterior pituitary and just talking about all of the other glands in the body. So we're going to continue with our story. We just talked about thyroid stimulating hormone. Now we're going to talk about thyroid hormone and the effects of thyroid hormone on the body. The first thing you want to know is that thyroid hormone is made from tyrosine. So your thyroid gland takes 2 tyrosine molecules, chops them up, and why is this not advancing? Hold on. There we go. Takes 2 tyrosine molecules, chops them up and glues them back together, and you get this. What you want to notice, yes, sorry, just checking my next slide, is that your thyroid hormone has iodines on it. There are two versions of thyroid hormone. You have one version with 4 iodines, that is tetraiodothyronine, and one version with just 3 iodines on it, that is triiodothyronine. You are never going to have to write either of those. When it comes to writing on either the lab exam or a lecture exam, you can simply say thyroid hormones. But I might ask you about the difference between T4 and T3, so you do want to know that they exist. So as this says, T4 is the major product of the thyroid gland, which means that most of what the thyroid makes is T4. So mostly T4 comes out of the thyroid gland, some T3. Most T3 is converted to T3 in the tissues by what are called deiodinases. So you have higher levels of T4 circulating throughout the bloodstream, and then that gets converted to T3 in the tissues. And then T3 is the more active form of the hormone, meaning it binds to the receptor better. It's sort of like if you have a key made for one of your doors or your car, and the new key doesn't work as good as the old key, like they both start the car, but one key works a little bit better. T3 is the key that works a little better. It's just better at activating the receptor. So that's all we're going to do about thyroid hormone production. We're not going to worry about this little bit right here, even though I think it's cool. All right, so what does thyroid hormone do? Thyroid hormone does a lot, and it also depends on how old you are. For adults, we are primarily just going to say that thyroid hormone regulates metabolism. It increases your overall metabolic rate of your body. You will burn more calories in a day if your thyroid hormone levels are higher. It plays a role in blood pressure, tissue growth, and reproduction, but we don't have time to get into any of that. So we're just going to think of it as promoting metabolism. During development, in utero and the first couple years of development, it is absolutely required for proper brain development. So then what happens if you don't have enough? What happens if you have too much? We're going to start with homeostatic imbalances in adults and then talk about homeostatic imbalances, too much or too little, in kids. So if you have hyposecretion, not enough thyroid hormone, regardless of why, it could be that you don't have enough iodine in your diet, or maybe you've got Hashimoto's, which is an autoimmune disease. Either way, this primarily leads to mental sluggishness, weight gain, and fatigue. If you are hypothyroid for an extended period of time, you can develop a goiter, which is an enlarged thyroid. And that happens when your thyroid gland is exposed to elevated TSH for a long period of time. So if you're hypothyroid for years, your pituitary just keeps on churning out thyroid stimulating hormone, and you get elevated levels of thyroid stimulating hormone for years. And when your thyroid is exposed to that, it starts to grow in an attempt to make more thyroid hormone. So in adults, if it's treated, which it's easily treatable in adults, you either give somebody some iodine pills or you give them some thyroid hormone replacement therapy. All of the symptoms are reversible, except for the goiter. That's an extreme symptom, but the sluggishness, the weight gain, and the fatigue are reversible. If left too long, some of the symptoms become permanent. Then, if you have too much in adults, this might be Graves' disease, which is a different autoimmune condition. Now your metabolism is going to be too high, so you're going to have weight loss, you're going to be sweating, And now your mind is going to be racing a little bit. You're going to have ADH-like symptoms. You can get, I don't know if you can see very well in this picture, this guy's eyes are bulging a little bit. That is called exophthalmos. I don't know if exophthalmos is reversible, but the weight loss, sweating, and ADHD-like symptoms are reversible. They can either take out your thyroid gland, they can put you on anti-thyroid medication, or they can give you a radioactive iodine cocktail, and your thyroid gland concentrates the iodine, so you get so much radioactivity in one small part of the body, and it just burns out your thyroid gland. Then we have infants and children. As this says here, generally not a problem to have too much thyroid hormone, or it usually doesn't happen that an infant or a newborn will be exposed to elevated levels of thyroid hormone. However, if you have decreased levels of thyroid hormone, either as a fetus or as an infant, this can affect your brain development. As early as 2 weeks, you will start developing cognitive deficits. If this is treated early enough, again, it's easy to treat. You either give the child or the mother thyroid hormone replacement therapy. If that starts within the first couple of weeks, then even if that child had a thyroid hormone deficiency in utero, they catch up with their peers after a couple of years. Left untreated, this leads to severe permanent cognitive deficits, like this person right here, shortness of stature, digestive system problems, cognitive deficits. This suite of symptoms is called cretinism. And that's what happens if you're hypothyroid as a child and then it's left untreated into adulthood. And again, we're skipping these. How are we on time? We're 22 minutes in. We're doing good. So now we are still in the thyroid gland. We're talking about calcitonin. It is produced by the parafollicular cells of the thyroid gland. There are two things primarily that you want to know about it. It is released when your blood calcium levels are elevated, and it lowers your blood calcium levels. Apparently, it's not all that important, because when you remove somebody's thyroid gland, you also remove their ability to make calcitonin, and most people don't have problems with calcium without their thyroid gland. Your parathyroid glands you do need. They secrete parathyroid hormone, and they're located right here on the back of your thyroid gland. Hey, let's just for fun, let's do red. There we go. There's your thyroid glands. Or excuse me, there's your parathyroid glands. So what does parathyroid hormone do? It is released when your blood calcium levels are low, and it increases your blood calcium levels. How does it do that? Well, there's 3 ways down here, and they're each pictured up here. So it breaks down bone matrix, so your calcium goes from the bone into the bloodstream. It increases the reuptake of calcium from your urine, so you retain more calcium, you're not peeing as much out. And it increases the absorption of calcium in your gastrointestinal tract. So 3 different ways of maximizing blood calcium levels. Then we are on to the adrenal gland. Let's just do a few minutes of the adrenal gland. We'll do one hormone in the adrenal gland and then we'll stop. I don't want to leave too much for the last day, but we're in pretty good shape here. So the adrenal gland we haven't covered yet. I was going to say you may recall. Actually, you may recall from Anatomy and Physiology 1, it has 2 layers. This inner part here, which I am now coloring red, is the medulla, and then this outer region here is the cortex. The adrenal medulla I consider part of your sympathetic nervous system. It is made out of neural tissue. It's the same neurons that make your ganglionic fibers or postganglionic fibers in your sympathetic nervous system. And then the cortex, the outer layer, is the part of the adrenal gland that is traditional glandular tissue. So it's made out of the same kind of tissue as your thyroid and your pancreas. So we are going to be focusing primarily on the adrenal cortex and just talking about two hormones, aldosterone and cortisol. We'll do aldosterone first. So there is a group of hormones that come out of the adrenal cortex called mineralocorticoids that help regulate your electrolyte levels. Electrolytes in the wild are rocks. Well, they're not rocks. They're bound up in rocks, but we call them electrolytes. You have a whole group of hormones that regulate them. The only mineralocorticoid we care about is aldosterone. Aldosterone, and by the way, if you've drifted off, come back, because aldosterone is really important. Aldosterone is your most important electrolyte regulator. It stimulates the reabsorption of sodium in your kidneys, and if you retain sodium, you also retain water. So what aldosterone is really doing is helping to maintain your blood volume and therefore your blood pressure. So it is a major regulator of blood pressure, very important to maintain adequate blood pressure. So the way it works is when your kidneys are making urine, or in your kidneys, you have tubules that are processing liquid that came out of your bloodstream. And those tubules are physically right next to a set of blood vessels. And there are cells that line the tubules, which you can't see here, that can pump solutes in one direction or another. So let's say you're going about your day, you're starting to get a little dehydrated. What aldosterone does is concentrate your urine. So as the urine is being made, oh, hold on. There we go. Aldosterone is going to cause sodium to be pumped from the urine back into the bloodstream. That means you're going to have an imbalance where now there's more sodium in your bloodstream than there was in your urine. And because your sodium levels are so low, you now have a higher concentration of water, right? If you pump all the sodium out, you leave a lot of water behind. If you leave water behind, this creates an osmotic gradient. So now the water is going to follow the sodium till it balances back out. And so now you've pumped sodium back in this direction, water has followed it, you've rebalanced the two, but on average or en masse, you've moved more water from your urine back into your bloodstream, concentrating your urine so that your blood pressure and your blood volume don't go any lower. I think we're going to stop there because 28 minutes for a screencast is a long time.